So today I've got this nice limit that comes from a 2001 issue of Mathematics magazine. So let's see what we have. So let's recall that the arithmetic mean of non-zero real numbers x1 through xn is, well, it's just their average. So you take their sum and then divide by the number of numbers that you have. Versus the geometric mean of the same set, well, you take their product and then you take the nth root if there are n numbers. And so now that we've recalled the arithmetic and geometric mean, so what is our goal? Well, we'd like to determine the limit as n goes to infinity of the geometric mean of 1 to the t, 2 to the t, all the way up to n to the t, over the arithmetic mean of the same set. Okay, so let's jump into it. So let's set L equal to just what I'll call our limit. So in other words, that's the goal that we're going for here. But let's notice that that tells us that the natural log of L is equal to the limit as n goes to infinity of the natural log of that geometric mean minus the natural log of the arithmetic mean, where I've just left off of the set. I think we'll just leave the set as being understood. Okay. So the first thing that we want to do is consider this term right here. So in other words, the natural log of the geometric mean. So let's see if we can get a handle on what that looks like. Okay, so natural log of geometric mean. I'll put the numbers in here now. So 1 to the t all the way up to n to the t. So that'll be the natural log of the nth root of 1 to the t times 2 to the t all the way up to n to the t. So that's, again, just by the definition of the geometric mean. But now what we can do here is use logarithm rules to simplify this a little bit. So observe that that's going to give us something like this. We'll have t over n times the natural log of 1 plus the natural log of 2 added all the way up to the natural log of n. And again, that's because a natural log turns a product into a sum, and then it turns exponentiation into multiplication. So that's exactly what we have going on here. Okay, but seeing a sum like this makes me think about a Riemann sum. And so, in fact, in this case, it looks like a Riemann sum of the natural log function. So let's get a picture of the graph of the natural log function on the board right here, and then we'll talk about a Riemann sum associated to that. Okay, so there we've got a picture of the natural log, or the graph of natural log on the board. And then I've also got an approximation of the area under the curve by these yellow rectangles, where I've taken the height of the rectangles to be the left-hand endpoints. So notice the first rectangle has a height of 0, but 0 is the natural log of 1. The second rectangle has a height of natural log of 2, the third natural log of 3, so on and so forth. But let's observe that the area of these rectangles, if we take them all the way up to n, is exactly this geometric mean right here. Well, that's not totally true. It's exactly this part in here that's being summed up of our geometric mean. Because note, we've got natural log of 1 plus natural log of 2 plus natural log of 3 all the way up to natural log of n. Well, let's notice that the sum of the areas of these rectangles is exactly what's going on here. Well, that's actually not totally true because we're taking left-hand endpoints, and we're taking left-hand endpoints on the interval from 1 up to n. So that means the last rectangle will have an endpoint of n minus 1. So that means we've got this extra term here. Okay, but that's okay. We can take care of that. And so notice that the area under the curve is definitely larger than the area under these rectangles, because we've got all of this bit here that we're missing. So that means that we can put the natural log of our geometric mean below the integral, which is of this natural log function. Recall that this was the graph of the natural log function. Well, at least multiplied by t over n, because we're just talking about these yellow rectangles corresponding to this yellow underline. And so what is that? So this is going to be t over n, And then we'll have this natural log of n, which we have to add on because, again, since this is an approximation by left-hand endpoints, we're missing that one. And then plus our sum from 1 to n, sorry, our integral from 1 to n of natural log of x dx. Okay, so that's where we are there. But now let's approximate this by rectangles with right-hand endpoints. And maybe we'll do that in this magenta color. So that would be like a rectangle like this. And then the next one would be a rectangle like this. And then the next one would be a rectangle like this, and then so on and so forth. But notice those rectangles will overestimate the sum. But those rectangles are exactly what we have here. So those also include this natural log of n, whereas this natural log of n was, like I said before, missing in the yellow rectangle case. Okay, so let's maybe note that the area under the curve is smaller than this magenta, but again, this magenta is exactly what we have here. So here we can say that our natural log of our geometric mean is bigger than or equal to t over n, and then the integral from 1 to n of natural log of x dx. So there, we've bound the natural log of our geometric mean between two things that involve the integral of the natural log. Now, let's see what we can get out of that. Okay, so this is the inequality that we built on the last board, and now we'd like to simplify this to get the integrals out of here. So let's see how we could do that. So both of these involve the integral from 1 to n of the natural log of x dx. So the real question is, how do we do that integral? Well, we're going to do it with integration by parts. So the trick is to take u to be the natural log of x, and dv is simply dx. But that means that du will be equal to dx over x, and that means v will be equal to x. And so using the standard rule for integration by parts where you have the integral of u dv is u times v minus the integral of v du. So here we're going to have u times v, that's x natural log of x, minus the integral of v du, but that's just the integral dx. And then we've got all of these bounds from 1 to n in all of the cases. Okay, so I forgot my t over n there. Let's get that in there. And let's see what we have. So this is going to give us n times the natural log of n. But natural log of 1 is 0, so that's gone. And then we'll have minus n plus 1. And that's because the integral of 1 to n dx is just going to be n minus 1, but then we've got this minus sign here. Okay, so let's see. That means that we could take this term and replace the integral with what we have and maybe move some things through if we'd like to, and we'll have something like t times the natural log of n minus t and then plus t over n. So that's what we have in the bounding below here. And then let's see what we have over here. So here we're going to have t over n times the natural log of n. That just comes from the non-integral part. And then we'll have plus, well, this stuff right here. So plus t times the natural log of n minus t plus t over n. Okay, good. And again, like I said, that comes from expanding this out using that integral that we calculated. Okay, so now let's maybe get that summarized and then move on to an inequality for the arithmetic mean. Okay, so there's our inequality involving the natural log of the geometric mean, and now we're going to make a similar one involving the arithmetic mean. But we're just going to deal with the arithmetic mean directly first and then take the natural log of the inequality that we build. So the arithmetic mean of 1 to the t all the way up to n to the t. So that'll be 1 to the t plus 2 to the t added all the way up to n to the t over n. Okay, but now let's maybe think about this as 1 over n times that. Well, that's obviously the same thing, but that allows us to think about this as an as an approximation of our integral. So these will be values of a function, whereas these will be the delta x terms. And it looks like here we're taking the integral of x to the t, or at least this is a descendant of the integral of x to the t. So let's get a picture of the graph of an arbitrary x to the t on the board, you know, just as a mock-up, and see what we can get from that. Okay, so now we've got a graph of the curve x to the t on the board, and we're approximating the area under the curve between 1 and n with rectangles of width 1 and height given by the left-hand endpoint. But notice that that's going to give us a rectangle with height 1 to the t here, 2 to the t here, all the way up to n minus 1 to the t here. But that's almost every term. It's every term that we have here except the n to the t term. And, well, we're approximating too small. So that means the real value of the integral will be larger. And so that sets up the following inequality. So our arithmetic mean will be bigger than or equal to 1 over n times the integral from 1 up to n of x to the t dx plus n to the t, where we have to add on that extra n to the t that we're missing from these rectangles. Okay, so now let's play the same game with right-hand endpoints. So that'll give us a rectangle like this right here, a rectangle like this right here. The next one will be something like this, and then all the way up, the last one will be something like this. So now we're overestimating the area under the curve. And furthermore, if we're looking at the integral from 1 to n, well then we don't even have this bit down here. So that means we'll have to add that in as well. So let's see, this is going to be now, the arithmetic mean will be bigger than or equal to 1 over n, and then times 1 plus the integral from 1 to n of x to the t dx, where I had to add that 1 in from this rectangle that we had to include. Okay, so let's integrate this out to see what we have. So here we'll have a 1 over n, and then we have 1 plus, so we'll have x to the t plus 1 over t plus 1 evaluated from 1 to the n. So that's less than or equal to the arithmetic mean, which is in turn less than or equal to 1 over n times n to the t plus x to the t plus 1 over t plus 1 evaluated from 1 up to n. Okay, so let's see what we get. So plugging this in, we'll have 1 over n plus, so let's see, it'll be n to the t over t plus 1 minus 1 over t plus 1. So that's after moving this 1 over n through, and that should really be 1 over n times t plus 1. Okay, so that's less than or equal to the arithmetic mean, which is in turn less than or equal to n to the t minus 1. And then we'll have plus n to the t over t plus 1, and then minus 1 over n times t plus 1. Okay, great. So next up, what we want to do is take the natural log of this. So let's do that on a clean board. Okay, so this is what we've got so far, and now we'd like to maybe simplify it a little bit or combine some terms and then also take the natural log. So let's maybe focus on this left-hand term first, which I'm underlining in magenta. So let's start by putting these terms together. Notice our common denominator will be n times t plus 1. Or maybe it's just t plus 1 if I take this 1 over n and write it as n minus to the minus 1. Okay, so let's see. We're going to have n to the minus 1 times t plus 1 over t plus 1. So that's giving that the common denominator. And then plus n to the t over t plus 1, and then minus n to the minus 1 over t plus 1. Okay, great. But now let's see if we can smush this together to something a little bit nicer. So we'll have, let's see, n to the minus 1 times t. That's from combining this term and this term. Notice that the plain old n to the minus 1 term cancels. And then that'll be plus n to the t over t plus 1. Okay, so that's the magenta term. Okay, and then maybe the blue underlined term, let's see what we get out of that. So I'll put a blue box to say that that's where we're doing this calculation. So kind of similarly, we'll have a denominator of t plus 1. So in this case, we'll have n to the t minus 1 times t plus 1 plus n to the t minus n to the minus 1. And then this is all over t plus 1. So we've got something like that happening. And then let's see how we could simplify this, maybe taking the natural log. Well, first, perhaps let's factor an n to the t out of this, just because I think that's going to play an important role. And then we'll be left with n to the minus 1 minus t times t plus 1 over t plus 1. And then perhaps we could take the log of this, and we'll see that we get t times the natural log of n plus the natural log of all of this other stuff, which is n to the minus 1 minus t times t plus 1 over t plus 1. Okay, so that's what we've got for this term right here after taking the log. And then, well, what about this one on the other side? Well, again, we could take an n to the t out of this entire thing, and that's gonna leave us with n to the minus 1 times t plus 1 plus 1 minus n to the minus 1 minus t, and then that's all over t plus 1. And then again, taking the log of this, we'll have t times the natural log of n plus the natural log of, well, all of that stuff that's left over. Okay. So now let's get that written up on the board, and then we'll maybe take it home. So this is what we got up to on the last board, although I've multiplied by a minus sign and switched the inequality, because let's recall that we really want an inequality involving natural log of geometric mean minus natural log of arithmetic mean, because our goal is the quotient of those two with no natural logs. And getting it set up like this is nice, because now we can just add straight down, and we'll, like I said, have something pinning both sides of that difference. Okay, so let's do that. So like I said, in the middle, we'll have the natural log of the geometric mean over the arithmetic mean, because that's the difference using logarithm rules. And then on this left-hand side, well, let's see what we get. Well, some stuff nicely cancels. Notice that here we have a minus t natural log of n, and here we have a t natural log of n, so that cancels. Okay, so that's good. And then after that, we'll have a minus t plus t over n, and then minus the natural log of a bunch of stuff. So let's see, that'll be an n to the minus 1 times t plus 1, and then minus n to the minus 1 minus t over t plus 1. Okay, great. And then let's see what we get over here. So again, something cancels. Well, maybe the worst term, if you will, cancels. This t times natural log of n term cancels. And that's going to leave us with t over n minus t over n times the natural log of n, and then minus t plus t over n, and then plus this natural log of, or that should be a minus, so minus this natural log of t times n to the minus 1 minus t plus 1 over t plus 1. Great. But now that we've pinned this between two places, we can take the limit, and hopefully the limit of both sides will give us the same thing, and we can apply the squeeze theorem. Okay, so let's see, the limit of this left-hand side. So again, this is the limit as n goes to infinity. And as we'll see, we'll have to include some assumptions about t, which we haven't introduced yet. But I think it's nice to introduce them at the end so we see exactly what we need. Okay, so anyway, as n goes to infinity, well, this minus t will stay the same. So we have a minus t. And then notice that this t over n will go to 0, no matter what t is. And then we'll have minus the natural log of some stuff. Well, so notice n to the minus 1 will go to 0. So let's just sketch this off going to 0. So that's going to 0. and then n to the minus 1 minus t will also go to 0. And that's because now we're including this assumption that, let's see, I think t has to be, well, bigger than -1, but maybe we just take it to be bigger than 0 to be safe. So anyway, that's going to go to 0, but then that's going to leave us with the natural log of 1 over t plus 1. Okay, so that's what we've got at the moment. And then that's going to be less than or equal to the limit as n goes to infinity of the natural log of our gm over am, and which is in turn less than or equal to what's going on this side. So let's see what happens to this as n approaches infinity. So let's see, as t over n times natural log of n, what happens to that? Well, that actually requires a little bit of work, but it's pretty easy with L'Hopital's rule to see that this goes to 0. And then this t over n term will also go to 0. And then this t times n to the minus 1 minus t will go to 0 as well, leaving us again with minus t minus the natural log of 1 over t plus 1. But now we're ready to start putting this together. So notice that I can take this minus sign here, turn it into a plus if I take this 1 over t plus 1 and turn it into a t plus 1. Furthermore, I can do the same thing over here. So minus to a plus, and then this turns into t plus 1. And then I can take this minus t and write it as the natural log of e to the minus t. Then I can do the same thing over here. So this is also the natural log of e to the minus t. But now we've got the both sides of the same. So that means that the limit is equal to, well, either of the sides are the same. But then we can smush those together using logarithm rules, and we'll get the limit as n goes to infinity of the natural log of the gm over the am is equal to the natural log of t plus 1 over e to the t. Just again, pushing those together. But if the limit of the natural logs is equal to, well, this natural log, well, then that means that the limit of our original question is, well, the same thing without the natural logs. So in other words, t plus 1 over e to the t. And there we have it. We've just determined this nice limit. And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.